The bottom of the Aegean Sea is a graveyard for human history. Left alone in the dark, the ocean swallows everything we leave behind. This chart shows the accepted timeline of human mechanical engineering. Notice the flat line through antiquity. The line only breaks upward during the Middle Ages, right around the year 1300, when European clockmakers began developing complex gear trains. But in the spring of 1900, a crew of Greek sponge divers was blown off course by a storm. They anchored near the island of Antikythera and stumbled upon a massive sunken Roman cargo ship. Down there, they found exactly what you'd expect from the ancient world: marble figures, glassware, and stunning bronze statues. Among the haul was a corroded, calcified lump of bronze and wood. It looked like ordinary ocean debris, and the recovery team largely ignored it. That changed in May 1902. An archaeologist working in Athens noticed the rock had dried out and split open. Sitting inside the stone were precise, triangular gear teeth, a level of mechanical engineering that simply did not exist in ancient Greece. The physical existence of this artifact breaks our model of technological evolution. We have to figure out how it got there. Researchers immediately ran into a physical problem. The device had fractured into 82 distinct fragments. The bronze was so brittle that trying to manually clean or pry it apart would destroy the very evidence they needed to study. The solution arrived more than a century later. In 2005, a specialized research team used high-resolution 3D X-ray computed tomography to look straight through the calcified shell without ever touching the metal. The scans revealed a dense, microscopic labyrinth. 30 separate, precisely interlocked bronze gears were sitting right underneath the stone crust. To understand what this machine did, we have to stop looking at it as an archaeological artifact and start treating it like a machine, tracking exactly how kinetic energy moves through its internal architecture. The entire system runs on a single physical input. The user simply turns a hand crank on the side of the machine's wooden casing to set a specific date on the front calendar. This animation illustrates the core astronomical problem the ancient engineers had to solve. The moon's orbit is elliptical. As it moves closer to Earth, it speeds up, and as it moves away, it slows down, a phenomenon known as Keplerian motion. To translate that variable speed into metal, they designed a brilliant pin and slot mechanism. They linked two overlapping gears slightly off-center from one another. A pin on the bottom gear slides back and forth within a cutout slot on the top gear. When you apply constant rotational energy to the first gear, the offset pin slides through the slot, forcing the second gear to systematically accelerate and decelerate. They replicated orbital physics in bronze. That specific piece of engineering separates this device from a standard clock. It calculates nonlinear physics, making it a true analog computer. The energy from that single hand crank splits off into a highly complex system of parallel gear trains, calculating a massive array of astronomical data simultaneously. The front dial tracked the exact position of both the sun and the moon as they moved through the zodiac. Surrounding that was a 365-day calendar dial, complete with a mechanical adjustment to account for leap years. The front face also featured a miniature half-black, half-white sphere that physically rotated in place to display the current lunar phase. The back of the device zoomed out even further. These dials calculated massive, multi-decade celestial cycles, while a smaller dial tracked the social calendar, indicating the precise timing of the Olympic Games and other pan-Hellenic festivals. This diagram illustrates the lower back dial, which mapped out the Saros cycle. This is an 18-year geometric pattern used to track and display predicted eclipses, long before they actually happened. Tiny text inscriptions on the metal told the user exactly what kind of eclipse was coming, solar or lunar, and the specific time of day the sky would go dark. The user simply turned a handle and the machine processed the chaotic, interacting variables of the solar system, delivering the answers on the side of a portable wooden box. Beyond the math, we have to look at the manufacturing reality. The average distance between the gear teeth inside this device is just 1.6 millimeters. You do not wake up one day and cut millimeter-perfect metal gears by hand. Achieving this level of microscopic precision requires a deep, multi-generational tradition of engineering. This was a mature technology, not an isolated prototype. When that Roman ship went down in a storm off Antikythera, and the ancient world subsequently fractured, this entire discipline of science sank with it. The knowledge was completely erased from the Western world. Engineers were forced to start over. It took more than 1,400 years of blind, halting effort for humanity to successfully rediscover the mechanical principles that were already spinning inside a wooden box in 60 BC. The Antikythera mechanism is a physical reminder that human progress is not a guaranteed upward line. Centuries of hard-won advancement can easily be swallowed by the sea, leaving us to slowly invent the wheel all over again.